So while amantadine is no longer really used in the market, we have other antiviral agents for the treatment of flu that are much more effective. And so they're all based on the same principle. They are neuraminidase inhibitors. Let's look a little bit more detail how it works. So we already went through the process of viral budding from the host cell. And so here is the capsid that is being self-assembled in proximity to the host cell membrane. And basically as it buds, it takes with it the nucleic acid and also the envelope, which is the bilayer of the host cell containing two viral proteins, hemagglutinin in green and neuraminidase, which is the enzyme in red. As the virus buds out, hemagglutinin is still binding to the receptor, which is sialylated and which is the target of the virus. And so in order to have a release of the viral particle, neuraminidase has to cut off the bond between the sialic acid and the rest of the receptor, thus releasing the new virons. Okay, so the active site of neuraminidase is known. We do have the crystal structure of the enzyme with the sialic acid inside. And what we can see here is that several interactions are in charge, basically are devoted to stabilizing this. First of all, also in the active site, there is space for water. Okay. The other thing that we can notice is this bidentate hydrogen bond between the carboxylate on sialic acid and an arginine. And then various other polar interactions, again containing several arginines as well as negatively charged residues. So what's the mechanism of action? So we have sialic acid in the chair conformation that is just more stable. When it interacts with enzyme, we have the stabilization of these pseudobond conformations. In other words, the enzyme, by forming this bidentate hydrogen bond, changes the conformation of the sugar and stabilizes a conformation that otherwise would not be particularly stable. Now, also note that the hydroxy group to which the protein is attached, so the rest of the protein in the glycoprotein is this one. And so that goes to either a serine or threonine on the glycoprotein. So in the first stage, again, we have binding, recognition. In the second stage, we have several things happening. So basically this binding stabilizes the not so stable conformation of pseudobond conformation, and then there is also water in the active sites. So we have protonation of the ether moiety here, which is again what keeps the sialic acid attached to the glycoprotein. And so as this oxygen gets protonated, we have a rearrangement of the electrons here. So from the oxygen geminal to the ether, we have an electron pair that forms a partial double bond, and also we have release of this ether group as alcohol. And here is another view of the transition state, where this bond is now planarized, this area here. And again, as the new bond forms, the new carbon-oxygen bond forms, there is a carbon-oxygen bond that breaks here, releasing the glycoprotein. So in the next step, we have the free glycoprotein here, released out, and again, still stabilized by interactions within the active site of the enzyme. We have the water that had been deprotonated to a hydroxy group. And then this hydroxy group in turn attacks the planarized sugar, and particularly the carbon-oxygen bond, where there is a positive charge on the oxygen here. And so attack of the lone pair on that carbon rearranges everything out, and we form this other transition state that leads to release of the sialic acid, right? So now again, the hydroxy group attacks here, everything is released, and it's released at alpha anomer, which is not the most stable because the the biggest group, the carboxylic group, is in the axial conformation, but within the enzyme that then goes on to the beta anomer. Okay, so we have first, attacked the sugar to the in the active site of the enzyme with that arginine. Then we have planarized the sugar, released the glycoprotein, and finally released the sugar from the active site. Neuroaminidase inhibitors then are based on this general structure and contain this group, oxygen double and the carbonate double bonds. So this is pretty much the starting point for the design of all the inhibitors. So we have to have this distorted conformation of the cyclohexane. All right, so we started with, designing these analogs with, several things that looked useful, like this DANA and FANA. And finally, what we have on the market now is Danamir and oseltamivir, which are the most potent ones. So the design of these two transition state analogs went through a lot of modeling, and your book has a pretty lengthy explanation of the whole history of the transition state inhibitors, starting from the 6 carboxamides and going to the carbocyclic analogs, in which basically we lose the oxygen, like in oseltamivir. What I would like you to remember is simply that we conserve this planarity of the structure that we have in transition state. And in the next video, we'll go through in more detail on how Rolenza was developed.